Hello, my name is Robert Shillito. I'm a student at NC State University, and for my ECE535 demo project, I decided to build a permanent magnetic bearing. I decided to build a magnetic bearing because I found the topic very interesting when we discussed it in class, and I wanted to know more about it. I realized after researching the topic that I didn't have the time to complete an active magnetic bearing demonstration project, as it requires complex feedback control systems. So I decided to build a permanent magnetic bearing as a demonstration of the magnetic bearing concept and the forces between permanent magnets.
This SOLIDWORKS model shows the essential components in my bearing, the magnets. There are 6 sets of ring magnets around a set of large ring magnets in the center. The final assembly has an axle threaded through the set of large ring magnets in the center. These magnets are all polarized on their ends and act in repulsion. This 2D FEMM simulation will help to illustrate how the magnets repel each other. The B field lines loop around each magnet as they return to their opposite pole. The field lines repel each other because they are all pointing in the same direction. The force between two magnetic poles can be calculated from the magnetic form of Coulomb's law shown here. However, this equation only works for point magnetic monopoles. Since all magnets are dipoles and have a distributed magnetism, this equation is only useful in a small set of specific circumstances. This equation can be used to calculate forces between real magnets, but it considers magnets as dipoles where each pole is a point. It is useful in cases where a magnet is farther away from another magnet than the separation between the magnet's own dipoles. To calculate forces for magnets that are close together and or have complicated geometries, a numerical solution tool should be used. A concept we need to understand when discussing how magnetic bearings work is Earnshaw's theorem. This theorem essentially describes why a magnetic bearing built only from permanent magnets will not be stable. My bearing demonstrates this and requires an actual physical contact point to stabilize the system. Without this physical contact point, the axle will be pushed out of the bearing.
Here is the fully assembled demonstration project. I built 2 bearings to hold each end of the axle. These are the bearing frames holding 6 sets of 4 outer ring magnets for each bearing. This is the axle holding a set of 4 larger ring magnets inside each bearing. I used these threaded steel rods for the axle and to hold all the frames together with nuts. The end plates on each end are cut from the same template as the bearing frames, but with smaller center holes. They each hold a bolt with a lens glued to it here. It provides the physical point of contact required to keep the axle inside the bearing. I used lenses from glasses and a hard plastic sticker here on the end of the axle to reduce the friction. Here you can see the axle and the rest of the bearing separated. Now we'll insert the axle inside the bearings and you can see how the system is unstable as predicted by Earnshaw's theorem. And now that I have the axle inserted, you can see that the system looks stable. This is only because the axle is being forced out this end against this point contact. You will see the axle is pushed out of the bearing on both sides if I put a little bit of movement on the axle in this direction. Now that the axle is inside the bearings again, you can see that it's floating and only experiences friction at these point contacts. The magnets are repelling each other evenly all the way around the bearing. So I can press on the axle and it moves but returns to the center of the bearing when I let go. If I spin the axle, it spins easily and silently. The system isn't well damped, so it vibrates. You can maybe also see that it isn't balanced very well and doesn't have as low friction as I would like. It looks like the axle is too soft and is getting deformed when I spin it too fast, so it's becoming unbalanced. This makes the end points move around and increases the friction. I wanted to build another set of frames to compare my bearing with a typical ball bearing, but I ran out of time before I could do that. It seems to me to have lower friction than I would expect from a similar ball bearing design. So that's my demonstration of a permanent magnetic bearing.